Looks good. So our second speaker is Raja Appuswamy, and he will be talking about Accel-Align, a fast sequence mapper and aligner based on the seed-embed-extend method. Please.
Yes. Thank you very much, Lena. Hello, everyone. It's great to be here. I'm Raja Appuswamy, and I'm going to present our work Accel-Align today. This is work done in collaboration with Yiching Yan, who's my PhD student, and Nimisha Chaturvedi. So I'm preaching to the choir here when I talk about sequence alignment, because you guys have been working, the bioinformatics community has been working on sequence alignment for quite a while now. Essentially, the problem of sequence alignment is one that's extremely well known to all of us. So the modern sequencing machines are going to produce tens or hundreds of millions of noisy copies of the reference essentially at this point. And these copies are noisy because each read has potentially insertion, deletion, or substitution errors. The rate of errors is going to vary depending on the type of sequencing technology, of course. In this talk, and Accel-Align particularly focuses on short read sequencing technology, where we do get all these errors, but the rate of errors is much lower than long read technology like the previous talk. So since we have the possibility of insertions or deletions in the read, we have to rely on edit distance or Levenstein distance for comparing the read to the reference and for aligning the read to the reference. We also, most of us here also know about the complexity of the computational complexity of edit distance. There is a very celebrated theoretical computer science result, which is called the Smith conjecture, which says that subquadratic computation of edit distance is extremely unlikely. So we kind of know that the solutions that we have for computing edit distance are potentially the best that we could potentially achieve. And despite several optimizations, we are at a point where edit distance need not be an order of n square. We could potentially apply optimizations to bring it down, but despite these optimizations, edit distance still remains substantially more expensive than the equivalent Hamming distance, where we could simply do a linear scan over two strings and compute the distance between the two strings. So in order to overcome the problem of edit distance, the computational complexity associated with edit distance, almost all aligners today, all gapped aligners today, which is by far almost all the popular aligners, they all use some variant of seed and filtering, seed filter and extend mechanism in order to minimize edit distance computation. And the core of this is pretty straightforward. First, you perform offline indexing of the reference genome. You can use a variety of different techniques for this. During the seeding phase, you're going to break up the reads into seeds, and you're going to look up potential candidate locations in the reference genome. The filtering phase is then going to eliminate unlikely candidate locations. And here is the most important part of basically making sure that you don't do unnecessary edit computations at candidate locations which are unlikely, right? So the filtering stage is going to be the one that's going to provide maximum improvement in terms of performance. And then finally, you have the extension stage where whatever comes out of the filter, you apply your edit distance based extension to determine your alignment score, your cigar, your mapping qualities, and all the great goodness, right? So given that this is the state of the art with all the aligners, and as the previous speaker also mentioned, where we are today is that very, very quickly, if you try to plot the amount of time taken by each stage, you will see that very quickly extension or edit distance computation starts to dominate the overall time, because that is the most computationally intensive aspect of sequence alignment, in fact, right? So this, given this is the state of the art, there have been some recent improvements in the theory, computer science theory side, which is of relevance to us, which is of interest to us. Particularly, a key improvement here, key invention here is the advances in randomized embeddings and randomized algorithms. So recently, about a few years ago, there was some work from Chakraborty et al., which we refer to as CGK embedding, where they actually proposed a mechanism, a very simple randomized algorithm that allows you to convert or move from edit space into Hamming space. So essentially, it's an algorithm that takes as input a string. In our case, it's a string that's going to be in the quaternary alphabet of ACGTs, right? So of length n. And you take another random string, which is a sequence of bits of length 3n. So you take these two things as input. As an output, what the algorithm does is it converts the original string into an embedded version, which is of length 3n. So you go from the original string of length n into an embedded string of length 3n. So that's what's shown in the example here. So you see here on the left, they could be your original strings. And the embedded strings essentially for all practical purposes, to simplify things quite a lot, what they do is they repeat characters from the original strings based on the random bit string. So some characters could be repeated twice or thrice, and some could be repeated just once or not repeated at all, and some could be repeated multiple times. So by using this randomized embedding algorithm, you're transforming the strings from their original representation into a new representation. And Chakraborty et al. Were able to show that by using the theory of random walks, you will be able to map edit distance in the original of the original strings into a Hamming distance computation on the new strings. More specifically, what they actually showed was that if you take two strings S1 and S2 in the original set with an edit distance E, there will be the equivalent strings S1 prime and S2 prime in the new set with the Hamming distance such that the Hamming distance of the new strings, the embedded strings, is going to be less than square of the edit distance of the original string with a very, very high probability. So essentially, this algorithm is going to allow you to map strings from one set into another set while preserving the relative distances between the strings. And given this improvement, the natural question that actually comes to mind is, can we use embedding to accelerate sequence alignment? So what we actually thought of was also a very straightforward approach where we go from seed-filter-extend to seed-embed-extend, right? So where we are using embedding as a filtering technique. So as before, we want to use seeding to identify candidate locations. And once we identify candidate locations, what we want to do is we want to apply embedding. More specifically, we want to embed the reference string at each candidate location, and we want to embed the read. Once we have embedded them, and I'm showing you an example here. So the read is shown here and a candidate location is shown here. And you see here the difference between the two is one character substitution. This could also be an insertion or a deletion, it doesn't matter, right? So you see on the right-hand side, the embedded versions of the two strings. Now, this one character change could be propagated into 5 or 6 character changes in the embedded string because you're using a randomized algorithm and a random bit string to determine the mapping between the original and the embedded string, right? But that doesn't matter. Once you have mapped the strings, you will now be able to compute Hamming distance over the embedded strings rather than using edit distance over the original strings. So the idea then is to use Hamming distance computations to compare the embedded read with every single embedded reference candidate and pick the candidates with the lowest Hamming distance. Once you have done this, you can simply extend the chosen candidates rather than having to actually go through many candidates and apply edit distance for many candidates. So some of the key aspects of this embedding-based filtering, which are interesting, is that the first thing is that it does not require prior candidate elimination. So the embedding-based approach is actually a selection-based filtering, right? In fact, you're selecting, it provides you a way to sort of rank the candidates, which is the second point, allows you a way to rank the candidates based on their approximation of edit distance. And then it allows you to select the candidates which have very low Hamming distance in the embedded space, right? So if you look at most of the other filtering techniques, which are which are elimination based, they're all going to be picking some kind of a metric which allows you to eliminate false candidates. It does not allow you to sort the candidates and pick good candidates, right? There are a few techniques which do selection based things, but they tend not to have very good accuracy. So majority of these, the filtering techniques tend to be elimination based, where you assign some kind of a threshold, or you use some kind of a metric that basically determines what candidates to eliminate, whereas embedding basically gives you a selection based filtering. And of course, there are no knobs or thresholds like K-mer counting or many pigeonhole based techniques where you need to actually fix upfront that I am going to tolerate E errors, and then I'm going to divide up the reads into these many compartments, and then if I have more than E errors, I cannot do anything, for example, right? So with embedding, you don't have any of those knobs. You simply take the read, take the reference location and embed them, and you can go ahead and compare, and you get a nice ranking. So the real question is, can we actually do this efficiently? Because if you're looking at 10 or 100 million reads, you're looking at about 1 billion embeddings of every read to a candidate, right? So assuming a read produces 10 candidates, for example. So that's a large number of embeddings that you have to do. Can you do it efficiently? And the second question is, I told you that embedding is a randomized algorithm. So is the randomized algorithm going to be accurate? What's the accuracy we are going to see in terms of mapping and in terms of downstream variant calling, for example? So to understand these things, that's precisely what we did. We actually went ahead and we implemented embedding in a new aligner called Accel-Align. And on the way, we implemented a few different optimizations to actually overcome the challenges I mentioned, particularly with respect to performance. One of the very first optimizations that we implemented was a new embedding algorithm, which we refer to as 2N embedding. So original CJK embedding from Chakraborty et al. converts a string of length n into a string of length 3n. We came up with a modified version of the algorithm that limits this embedding to a string of length 2n. And the algorithm here, I'm illustrating it pictorially. It's a very simple algorithm. So you have an input string on the top and the random string in the bottom, in the middle. So what happens in the embedding is if the random bit is 1, the corresponding character in the input string is going to be copied twice. Whereas if the random bit is 0, the corresponding character is copied only once. That's it. So in principle, this is the embedding, right? So it's still randomized because the random string is going to be generated randomly. But this algorithm converts every string of length n into a string of equivalent string of length 2n. Now, while we built this algorithm, there was concurrent work from Zhang et al., which actually showed that this 2n embedding actually has very similar distortion guarantees and lower bounds compared to the original CK embedding. And in our own algorithm, we actually see that for all practical purposes, the accuracy that we get with 2n embedding is the same as 3n embedding, and we get some performance improvement. So that was the first optimization that we did. The second thing that we did was improving memory and cache usage with pipelining. So I told you that we have to embed the read and every candidate location. And the goal of doing this is to be able to compute the Hamming distances. What we do is we collapse embedding and Hamming computation together, which should be something that should be very intuitive to you guys also, right? So we do it together in lockstep. And that way, we don't have to generate the entire embedded string. We can simply compute the Hamming distance without having to generate the entire embedded string. And this actually helps a lot because you're not trashing your cache by actually generating embedded strings, and you're able to keep track of these things in parallel, right? The third thing that we do, which is actually enabled by our pipelining, is prioritization and early stop. So instead of generating all possible embedded distances and then picking the best one, we can automatically track only the top k, right? In our case, we track only the best and the second best embed distance. As soon as a candidate's embed distance exceeds the second best, we can simply stop embedding. And as a result of this, embedding is going to stop very quickly for most candidates. And finally, we can also use embedding for computing the mapping quality. Rather than actually figuring out the top 2 candidates, extending both and using their alignment scores, it's also possible now to compute the embed distance of the top 2 candidates and use that for deriving the mapping quality. So this was just a point of interest to us because we wanted to see whether embed distance derived mapping quality was actually worse or better than an alignment score derived mapping quality. And that's what we did. And one of the benefits of this is that we now reduce the number of edit computations to just 1 per read for overall sequence alignment. So we have implemented all of these techniques that I described in Accel-Align. As I mentioned, we are targeting short read sequences for now. I'm just providing some basic details here. A lot more information is available in the paper. So Accel-Align uses a traditional hash table based indexing, and we use non-overlap seeding. So we don't do anything special in terms of seeding. In future work, we are exploring other seeding options, and we are going to look at relatively long k-mers because we are focusing on short read sequences once again. We are using libksw for extension in Accel-Align, which is also used by BWMM or Minimap. The table here shows you the time taken to compute the index and the size of the index. And I'm showing this here just so that you see that there is nothing special about it. So this is an offline computation phase, but the index size is about 13 gigabytes, which is fairly, it's about double the size of what Minimap actually does. Minimap actually has, or BWMM generates, but it's not too bad. For the hardware testbed that we use for the rest of the experiments that I'm going to show you here, we have a very simple setup, and we intentionally kept it simple to illustrate that we are able to push the limits of CPUs using algorithmic techniques like embedding, right? So we have a simple quad-core CPU with 32 gigabytes of RAM. So you already know that Accel-Align runs with less than 32 gigabytes of RAM, and many practice runs with 16 gigabytes even. And we have a simple 256 gigabyte SATA SSD. So the first result that I want to share with you is some data that we got. It's the data that we got using Mason simulated reads. So we generated 10 million 100 base pair pattern reads using Mason 2 simulator. And the table here shows you the execution time of a bunch of different aligners, which are very, very popular today. And the last column shows you the time of Accel-Align. Now notice here that we can actually run Accel-Align in both full alignment mode or in mapping mode. So in the full alignment mode, you generate the cigar and the mapping quality. Whereas in the mapping mode, you don't generate the cigar. You simply report the position together with the mapping quality based on the embed distance, right? And Minimap 2 can also be configured to be run in full alignment or mapping mode. So the key takeaway here is that Accel-Align is about 3 to 11 times faster than other aligners or other mappers just using plain CPUs without any special hardware or microarchitectural acceleration. To particularly focus on where this benefit comes from, I'm showing you here the result of various configurations of Accel-Align. So for this experiment, we are using 10 million 150 base pair pattern reads. And the first column here shows you Accel-Align where we don't do any embedding. So we are passing out all the candidates directly to extension, and we use KSW for extension. The second column shows you replacing KSW with wavefront aligner, which is a very new alignment alignment algorithm that has been designed, which is substantially faster than what was implemented in KSW. The third column shows you Accel-Align with embedding and KSW, and the fourth column shows you Accel-Align with embedding and WFA. So the key takeaway here that I want you to note is that replacing KSW with WFA gives you a 2.4x improvement in performance. So this is great that you get by using an optimized extension algorithm, but replacing, adding embedding with KSW gives you an 8.3x improvement. So embedding makes a huge difference, even if you are actually using an optimized extension. And the key takeaway here is that filtration is important, even if you have optimized extension, and embedding can actually provide very good filtration. So before I conclude, I just want to share a very quick result from a variant calling experiment that we did, and then I'll just wrap up. So in the variant calling experiment, we worked with GAAB high confidence variant calls and the NA12878 dataset. And once again, the performance that we observe is very similar to what we saw earlier. Accel-Align is about 3 to 10 times faster. The F scores are very comparable across all the aligners for both SNP and Intel variants. And we did notice that there's a fraction of, among the fraction of reads that are mapped, we have a slightly lower fraction of reads mapped because this particular data set uses very, very short reads. There's a lot more results in the paper, and I'm sorry I'm not able to share it here, but I highly encourage you guys to go and take a look at it. So to conclude, low distortion embeddings provide very new opportunities. These are exciting opportunities to map edit to Hamming space. Embedding can be used beyond sequence alignment, and we have actually used embedding in edit similarity joins for databases. And more recently in Project OligoArchive, we are using it for achieving read consensus in DNA data storage. And finally, I showed you that Accel-Align can provide a 10-fold improvement on CPUs. We are doing a lot of ongoing work in terms of optimizing the seeding, applying it to long reads, and so on. And I'd be more than happy to take any questions, and please reach out for feedback and collaboration.
Thank you for the talk. Now I see there are at least 2 questions in the Q&A panel, so let's try to get through them. So first, Ilya Minkin is asking that when speaking of the speed up, did you run the programs in parallel mode, and can embedding-based techniques be parallelized efficiently?
Yes, that's a great question. So absolutely. So everything ran in parallel mode. So we utilized the 4 cores, the quad core that we had, and embedding lends itself very easily to data parallelization because every candidate can be embedded in parallel and every read can be embedded in parallel. So it's a trivially data parallel operation.
Great. There's also another question. So Jan Fostier would like to ask that you mentioned the use of short, low error reads. What happens to the runtime when the error rate increases?
That's a great question. So in terms of embedding, the runtime does not change much. It's still linear in the length of the read itself. And in one of the applications I mentioned for edit similarity joins in databases, we have noticed that embedding can work with as high as 20% error rate. What we did notice is when we apply this to long reads, the bottleneck starts shifting to extension again, because at this point we are doing global extension, and we are looking into replacing that with eliminating the global extension and using chaining like what Minimap does.
Thanks. There's still several questions in the Q&A, but we are sort of running out of time. So Raya, you can also open the Q&A yourself, and it's possible to type your answers there. So absolutely, maybe you can do that for the rest of them, and we can move on with the program.